online workshop. Can you see the screen?
Yep, perfect.
Yeah, good. Okay, so today I will talk about a paper which has been published recently in collaboration with Sachiko Kuroyanagi about the possibility to test the quantum gravity with a stochastic gravitational wave background. So gravitational waves from inflation are one of the oldest signals we could in principle test from the early universe. And we have several experiments now that probe different frequencies of the spectrum. We have, well, the network of LIGO-Virgo-KAGRA, which is already operational, but then we have various proposals of missions such as LISA, or which has been approved, or SKA, the Einstein Telescope, and the DECIGO. In general, gravitational waves from inflation can leave this background of which is detectable in all directions, but its amplitude is generally quite small. This black line is actually the one predicted by Starobinsky inflation, the ordinary Starobinsky inflation. So as you can see, in general, the sensitivity curves of all these experiments, even DECIGO, if it will ever happen, will never be able to reach this background. For instance, well, okay, this is just what I said. The main reason is that the tensor to scalar ratio of the ordinary inflationary models, or even modified gravity models of inflation, in general is very small. So it's not detectable by interferometers. So in order to get a detectable signal, we would need to have a spectrum which is blue tilted. So something that even if it decreases at CMB scales, then it should increase with the frequencies and eventually reach one or more of these sensitivity curves. So the question is, since we cannot realize this scenario with a standard Zoro inflation, the question is whether we can, excuse me, whether we can do it with models inspired by, or motivated by, or embedded into quantum gravity. Okay, so in this talk I will not discuss phenomenological models of modified gravity. I will try to restrict my attention to something with a bit more of a theoretical motivation. Actually, there are many models, cosmological models of the market, which claim to be embeddable in quantum gravity, or at least share some of the features which we find in concrete quantum gravity proposals. But most of them, and there are actually many, usually predict a rather tilted spectrum. So they will not enter this talk because they don't give rise to an interesting stochastic background. And eventually it turns out that of these proposals, well, there are, I will talk about these 5, although there are more which are still under investigation. So this list does not pretend to be exhaustive. It's just what we could find among a plethora of models. I mean, these 5 models are actually 3 of them are due to Robert, and we already saw. He already talked about the 2 of them in his nice talk. The other 3 are the non-local version of Starobinsky inflation, then another model by Robert and collaborators about an inflationary, well, an inflationary regime happening in a non-commutative space-time, and then multifractional space-time. So all the content of this talk can be found in this paper with this preprint number. So let's start with Nonlocal Starobinsky inflation, which is perhaps closer to what we saw in day 2 of the conference. So it's I won't present the action here. So this talk is really cosmology oriented, but mainly the action is one of those actions you saw with non-local form factors, where the form factors are chosen in such a way that apparently there are no ghosts, at least at tree level, on the sitter. There was already debate about this point, so I think we already covered that part. I'm not really particularly interested now in opening that debate again. Here, the idea is just to see, okay, what are the cosmological predictions of this version of non-local quantum gravity? Can we see something? What type of signal could be observed? So let's go on with that and see what happens. So this model has been studied by several authors, many which are here. And it turns out that according to the slower approximation, in a local version of Alexei's model does predict a blue tilt spectrum at CMB scales. So the question is it can it reach also higher amplitudes at the higher frequencies? Okay, so this is just a slide recalling very quickly local Starobinsky inflation. So we have a quadratic action in the Ricci scalar, which can be re-expressed in terms of in the Einstein frame as Einstein-Hilbert gravity plus a canonical scalar field with a specific potential. And as we all know, it's in excellent agreement with the latest CMB observations. Oh, actually, I do show the action, sorry. It was bad advertisement on my part. So this is it. Well, this is just a recap of what we've seen in several talks. These higher order curvature terms in general introduced to improve the renormalizability of a theory, while the form factors are introduced, well, certain form factors are introduced to preserve unitarity, and also as a bonus to improve the renormalizability of the theory. Then, whether these claims are true or not in different backgrounds for different choices of form factors and operators here, well, that's what we've been debating, especially in day 2. These are the form factors that of a model, where Z is just the box divided by this fundamental mass scale, which is the one defining the scale of non-locality, and Z star is the Ricci scalar calculated on the de Sitter background. So basically, this is proportional to h squared. Okay, so these form factors depend also on another mass parameter, and when we send the non-local form factors to 1, basically we recover the Alexei's model. Okay. So these are the equations, the equation of motion for the graviton, or well, in this context, let me say a gravitational wave, and where the box and R are evaluated on the background, and this is the tensor spectrum, where epsilon is the first zero parameter, and the H2 tilde is the form factor usually defined in Minkowski, but where Z is shifted by that Ricci scalar term. This is actually important because this will change the overall behavior of this form factor, effective form factor H tilde. So several people calculated the first orders or observables, well, the tensor to scalar ratio, the spectral, the tensor spectral index, and we also calculated the tensor spectral running, the running of a tensor index, for reasons which will become clear soon. And as you can see, so the part in white is the ordinary expression for a local Starobinsky inflation, and the parts highlighted in red are extra terms coming from non-locality, as you can see if you increase the Slorov order, you will also increase these derivatives of this form factor. And where here capital N is the number of defaults. So on a quasi-de Sitter background, this Z star is almost a constant. And in general, well, you would expect that the Slorov expansion is well defined because higher order observables are suppressed as inverse powers of a number of defaults. Now, the spectral shape is affected by the expansion of the universe is affected by the spectral shape. So in general, the stochastic gravitational wave background is not just is proportional to the primordial power spectrum, but then there is also a transfer function which depends on the later evolution of the universe. And in general, if there is a reheating phase, this will affect the spectral shape. And of course, depending on whether we are in a radiation domination or matter domination regime, also this will be something that will enter the transfer function, and it will affect the stochastic gravitational wave background. And here the frequency in this talk is just proportional to the comoving wave number. Now, in standard Slorov inflation, it is customary to express the power spectrum as in a parametric form using the Slorov observables, in particular the spectral index and the spectral running. And of course, in general, the spectral running in the tensor sector is ignored because it's not really something we can observe with CMB data, but here we include it nonetheless. Now, yes, so here we took different types of form factors, which are basically those that appear in non-local quantum gravity, which are mainly Kuzmin form factor, Tombolis form factor, and then the stringy form factor, which I like to call it Watagin form factor, because Watagin was the first one to propose it in 1934. It's actually the first paper on non-locality as far as I know. And then there is the into the box squared proposed by Kalashnikov. Let's start with the Kuzmin form factor. It is one of those the so-called asymptotically polynomial form factors where P is a polynomial of finite order. Here we took just a monomial of order Q. And at first, well, we said, okay, let's compute the spectrum with this expression using NT. And we found this line going straight up to LISA frequencies. Great, this is a PRL. But then we were not happy, and we said, okay, let's add the tensor, running of the spectral index, and it decreased a bit, but still it was still quite high and reaching barely reaching LISA, but still crossing the strain curve of Einstein Telescope. But eventually we realized that the Slorov approximation does not work at the frequencies as high as those of interferometers. So what we did was to take the full expression of a tensor power spectrum and plot that, and the result is this red curve. So even if it is blue tilted for a certain range of frequencies, eventually it doesn't reach these amplitudes, and actually never reaches even the DECIGO sensitivity curve. So the reason is that all of these Slorov observables are augmented by those terms which I showed you before, and these corrections are not very small. So they are consistently small at the CMB frequencies, but they're not that small at interferometer frequencies. So you cannot really trust the parameterization of the power spectrum in terms of NT and alpha T. You have to take the full power spectrum. Okay, so this is basically the what happens. And well, we tried this for different values of m star, the mass of a non-local form factor, and different values also of the parameters alpha and q in Kurzmin form factor, but all eventually tend to the same curve, which is actually ordinary Starobinsky inflation. For the form factor proposed by Terry Tomboulis and proposed by Leonardo a few years afterwards, basically the same thing happens. The curves, as you can see, do change, but their fate remains the same, and they are well below any sensitivity curve. For the stringy form factor, or for the one by Krasnikov, the same thing happens, and eventually all of these models, all of them converge to standard Starobinsky inflation at high frequencies. So the main message of this part is that the blue tilt at CMB scales does not always mean a detectable signal at interferometer scales, because you can be blue tilted here, but eventually you do not gain enough power at the higher frequencies. And the analytic reason, if you're curious about that, is that for you can read it from the expression of a power spectrum in terms of the moving wave number, where the Hubble parameter here is the one of the ground solution of Starobinsky inflation. So while one term dominates at CMB scales, the other one takes the lead at interferometric scales, and eventually this means that all of those corrections, like exponentials of h tilde, h2 tilde, tend to 1 at high frequencies. And this is why all of these models, with no exception, lead to ordinary Starobinsky inflation at interferometric scales. Now let me, I don't know if you can read the titles, because I see the bar of Zoom.
Yes,
I hope
we can.
You cannot.
No, we can. It's fine.
Ah, okay, good, because I see. Okay, excellent. So the second model I will talk about was proposed by Robert and Ho a few years ago. And here the basic idea is that space-time, well, it was a realization of non-commutative space-time, so with the star products and all that, but made in such a way that the non-commutative relation between time and space was as simple as possible. Namely, it was a constant on the right-hand side, where t tilde here is not conformal time, but it's a summary definition of time, which is basically the integral of a scale factor instead of the integral of the inverse of a scale factor. Anyway, this is just a scalar field. The thing that changes is that the ground, which is non-commutative, and eventually this produces a modification of these low observables, and in particular, but only in the coefficient of those low observables. It doesn't add the new terms like in the non-local models we've seen before. Here, what changes is the value and the sign of the coefficients. So in particular, the tensor the tensor spectral index can be made positive definite if one chooses a particular ordering of the operators in the action. So, okay, that was just another example, and we just try to see what we will get from that. And the effect is very small. So the commutative case is, so this is natural inflation. Okay, it's another model of inflation. It's a scalar field with a cosine potential, and where A is the square of the energy scale in the cosine. Characteristic energy scale of this natural inflationary potential. So the dashed line is the standard case, and when you switch on non-commutativity, you lift it up to reach the sensitivity curve of DECIGO. So this is a case where we have a model which barely scratches the barrel and is able to reach the most sensitive of proposed experiments. Notice that DECIGO has not even been approved, so we don't even know if it will ever exist. Anyway, it's a possibility, and we wanted to explore that. So here the slow approximation is valid, so we don't have to take care to worry about to worry about high order slower terms, and we can use the parametric the parameterization of the power spectrum in terms of tensor index and its running. Now, another model we consider, actually this is a class of models, is multifractional spacetimes. It's something I've been working on the last 10 years. And it's a class of models. It's not really one, although these curves belong to one of them. They all have in common that the dimension of space-time changes with a probed scale by construction. So while this feature is common in all quantum gravities, all of them, including string theory, at the time I wanted to see whether implementing it by construction would help to improve the renormalizability of a perturbative quantum field theory. Anyway, that's another story. Here I'm concentrating on the cosmological part of one of these models, which is a local model actually, although later I will show you quickly a non-local, non-analytic model of the same class. Anyway, in this model, there is a parameter alpha, which is the Hausdorff or spectral dimension along spatial directions. And if you allow it for negative values while keeping the overall dimension to be positive definite, you can lift the inflationary potential, which had been calculated already a few years ago, up to DECIGO scales, if the running of a tensor index is 0. If you include the running, then things actually get quickly worse, and you lose a tremendous amount of power at high frequencies. Here, the reason why you can lift this potential, this amplitude, is that the effective, it turns out that in this model, the effective spectral index is alpha times nt. So if alpha is negative and nt is negative, this effective index is positive. While you do not change the sign of the running, because you have an alpha square in front of it. Also in this case, the slower approximation is valid. Then, if I'm not mistaken, because I cannot see the title, we considered the string gas cosmology, which we already saw in Robert's talk, so I will not repeat it again. Here, what happens is that you have a consistency relation between the tensor index and the scalar index, which makes the tensor index blue tilted if the scalar index, as we all know, is red tilted. Here we considered in the parametric expression in terms of nt and alpha t for the power spectrum, and we do reach the DECIGO fully. However, this probably is an artifact because okay, one problem of this model is that we do not have an exact expression of the temperature of a string gas in terms of a comoving wave number. So we cannot write down an analytic form of the power spectrum in terms of K. However, we have upper bounds, analytic upper bounds, and which are not very difficult to find, which are showed in dashed line. So the full expression of the power spectrum, whatever it is, should not really go beyond this dashed line at those frequencies. So since here we cross it, it means probably that this expression is not reliable at these frequencies. Okay, so basically this is what we could find.
Luca, you have 5 more minutes.
5 minutes, yeah, great. Finally, the new ekpyrotic scenario, the one Robert mentioned in the presence of an S-brane, respects the CMB constraints, because here one has a red tilted scalar spectrum and again the same consistency relation. So NT is not very big, contrary to the old ekpyrotic scenarios. And here we do find actually a large signal that can even reach the Einstein Telescope strain. However, notice that this curve would not be allowed by the BBN bound, which is this shaded region. So we have to take care here of the post ekpyrotic phase, and in particular about we have to take care of a reheating mechanism. Actually, in this paper in 2009 by Calcagni and collaborators, they showed that the presence of an early matter phase, namely a reheating phase, changes the spectral shape in such a way that at high frequencies the spectrum is the stochastic gravitational wave background. Sorry, is damped, and so one can basically avoid the BBN bound. So this means that this model in particular can reach the Einstein Telescope sensitivity curve while preserving the Big Bang nucleosynthesis bound. So as a summary, gravitational waves can become a powerful probe of the early universe. In particular, are a promising tool for inflation, but the amplitude of a stochastic background is typically small for standard slower inflation. We saw an example, non-local Starobinsky inflation, which predicts a blue tilted spectrum at CMB scales. However, it fails to give a detectable signal at higher frequencies, while other models of or motivated by quantum gravity can predict a signal detectable by DECIGO or Einstein Telescope, but very likely not by LISA. However, this is not, the list is not exhaustive, and there are other models under inspection. Let me conclude with a slide asking whether this is the only way gravitational waves can probe high energy or high curvature models. The answer is no. One can consider, for instance, the production of gravitational waves, for instance, in extreme mass ratio in spirals, or also the propagation of gravitational waves. In particular, one can place constraints on models with modified dispersion relations, or also via the luminosity distance of standard science. In particular, the luminosity distance of gravitational waves is sensitive to a dark energy content. So let me conclude this talk with an off-topic, actually, which is a model, a new model, possibly a new model of dark energy coming from a theory of multifractional spacetimes with non-local, non-analytic operators. This is a paper appeared, I think, last week, just last week. If I had uploaded before, I certainly have given a talk on this. But anyway, this slide will be enough. This is an action which reminds some of the non-local actions we've seen. However, it has been derived from first principles of multifractal geometry. So I was kind of surprised to find this action at the end of the day, because I didn't really have those RF1 of R plus Ricci, F2 Ricci plus Riemann F3 Riemann action types in mind. Okay. So this is a theory which features a fractional power of a D'Alembert, and well, you can check unitarity and renormalizability. Unfortunately, depending on the value of gamma, the theory is either unitary or renormalizable. You cannot have both things at the same time, because it's unitary. It is unitary when gamma is between 0 and 1. The theory is power-counting renormalizable if gamma is greater than 2, and is one loop actually not just renormalizable, is one loop finite And there is evidence that it's also finite at all orders if gamma is greater than 1, but different from 3/2 and 2. However, in this range, it is not unitary. So it is not a quantum gravity as we would like to have. However, we can still do physics with that. And the interesting thing, which was quite unexpected, is that for the extreme values, gamma going to 0 or to 1, it reproduces a whole class of non-local models of infrared gravity, where between curvature terms there are integer inverse powers of a D'Alembert. So since these models have been studied a lot, and especially in the context of dark energy, and they can actually, some of them can give rise to very huge deviation from GR, which can be tested by standard science in LISA, then one could be interested in studying this model also in this context. So thank you for your attention. I finish here.
Thanks a lot. So the floor is open for questions. I don't see anyone who's raised their hand, but let me ask a question going back to the first. Okay, no, there are questions. Well, let me still ask my question. So if you go back to the first model that you considered, then so is a way to understand the k-square scaling of the tensor spectrum simply the fact that you have, in your modification, you have a D'Alembert? Is that the origin of the k-square?
Where is the k-square?
At the beginning, you had you said that you got a k-square modification of the tensors. Instead of scaling variant, you had a k-square running. Or did I misread?
Okay, at CMB's case, you have quasi-scaling variance.
That's right. That's right. But then there's the correction term.
When you have a correction term, yes, which comes from the fact that this is a function of k because a z star is a h squared. So at horizon crossing, you have a k dependence from here. When you derive it, you get this correction. The same from all higher orders or
but it's
parameters.
Not a k-square correction term.
In general, it is not. It's much.
Okay,
Yeah. It depends on this h tilde 2, which for Kuzmin and Tombouli's form factor is extremely complicated. Right. While for the monomial form factors, it's just the power of h of the Hubble parameter divided by this mass scale.
Okay, Luca.
But in general, it's it's more complicated than k-square.
Maybe Zdrava can ask first because I think he's more related to this part, right? So
I'm just wondering, like, I mean, in the Tombouli's form factor, I mean, this polynomial p of z, there's a huge arbitrariness, right? So I'm just wondering, like, I mean, you can put any kind of polynomial and try to maybe there may be the blue tilt even in the high frequencies. Isn't it? It's impossible, or
what we did was to take the form factors that we knew that they would work for at least to make the theory ghost-free on this background. Okay, modulo all the debate we had in the previous days. So these form factors, as we're written here, are general. And so here one has to choose these E2H0 and E2H2. And what we did here was simply to take what is done on Minkowski background. So basically we took the four form factors mostly used. However, we also tried the combination of them because, for instance, you can subtract Kuzmin minus Kuzmin or Tomboulis minus Tomboulis, yeah. Forgive me for the jargon, with different coefficients, and that you can try to tune your power spectrum, but it doesn't work. in general, it doesn't work because all form factors which have better good properties about stabilities, in general, they all obey this asymptotic limit.
Yeah,
So I don't think you can play with that and find something interesting.
Okay.
But I cannot.
Another point, short point. I mean, you took this form factor. I mean, well, ideally, you should take the one in quasi-de Sitter one, right, on the other form factor, not the Minkowski one, because with other form factor.
No. The form factor itself is the one in quasi-de Sitter, because you can see here you have a Z star.
Okay.
Which is a zero on Minkowski, but is non-zero on de Sitter.
Okay, so sorry, I just overlooked this.
And then whatever you choose for your form factors H0 and H2, you also have this translation in terms of the Z0. So everything is consistent.
Okay. Thanks.
Okay, so I suggest we move on to the next talk. And I guess now there's a slight change in topic. So we are going from cosmology to UV completion, and